Sorry, what? No. The marks are in my head. You can look online. Yes, I can tell you. The marks are all in my head. I can tell you what you got. It's out of 5. Every question I just marked out of 1 mark. Yeah. Take a look in my head, or you can talk to me later. I will be returning them to you on Monday, and you guys can look at your corrections then. So here we go. Word equations. You stay on this page. I'm going to flip back. Earlier, when I first introduced to you guys the concept of chemical equations, I kind of brushed over the idea of what we're going to look at today. So chemical equations. A chemical equation is a statement that uses words or symbols, yada, yada, yada. And then I said, oh, look, there's word equations, but those aren't useful. So let's jump to the skeleton equations that actually let us do stuff. But very rarely are you going to actually be given a chemical reaction in this form. I want you on this page. I'm just flipping back to give today's lesson a little bit of context. I'm going back to give us context. Today is this is where I want you all sitting. Yeah. Are we good now? Yes, I flipped quick. So, I skipped over this idea that word equations exist, and I went straight to the skeleton equations. We learned how to balance those. And today we're going to go back and we're going to look at these word equations, because it's actually like when we speak about these things colloquially, or if I tell you we're standing in a lab and say, go grab this compound and go grab this compound, I'm not going to give it to you as a formula. I'm just going to use their names. When I'm talking about you guys, I don't describe you guys as the girl in the green hoodie or that kind of dark teal t-shirt dude over there. I use your names. People understand what your names are, and so we just use them. And so when we actually start to play in the lab, we're going to actually use the language of the lab. But you do still need to understand what all of the pieces are that make up what we're looking at here. Even then, this is not going to be the end. A little teaser into what we're going to look at Monday is stuff like this. Today's lesson is kind of the in-between. On Monday, I'm going to start giving you stuff like this, except this word shouldn't be pulsed, it should be placed. And so the language is going to look something like this. A piece of metallic zinc is placed in a Beloux solution of copper 2 sulfate. A reddish-brown layer of metallic copper forms in a clear solution of zinc sulfate. You guys are going to need to then take this 2-sentence description and boil it down to what actual chemistry is going on here. I just flipped ahead 2 pages. Don't leave this page. Stay on this page. I'm giving context for what's happening here. This word equation stuff, so we looked at balanced equations. The act of balancing those equations, wildly useful, absolutely necessary. It gives you actual amounts of things as you start to react stuff in the lab. It says, I need 2 of these and 3 of these, and I know it's going to produce 4 of those and 1 of those. The balancing is really important. This stuff is really important. We're talking about what's happening in the lab. I'm going to tell you, you're going to go to the lab. I'm going to give you some zinc. You're going to take the zinc, you're going to put it into a solution of copper 2 sulfate. That solution is going to be blue. Something is going to be produced. It's a red layer of copper, and you're going to get a clear solution of zinc sulfate. We'll talk about stuff like that. You'll actually go and do something like that. On the lab handout, that might be the description that I give you. And you need to take this description and turn it into a balanced equation to get an idea of what you've actually done. The in-between step is what we're going to look at today. This idea of how do I take the words, turn them into compounds with meaning properly. So, this is the page you should have all been on the whole time. I'm back here now with you. Sometimes you're going to be given word equations. More often you're going to be given paragraphs, but sometimes word equations. And you're going to be asked to create balanced equations. To do that, the names of everything is going to matter. which is why when I handed back your compound naming and formula quiz, I asked you to correct those, because you're going to need those skills today. What you're going to have to do to work with this stuff is you're going to have to turn each compound or element name into the right chemical formula. This is, this is the whole point of today's lesson, and this is it's what we did before with formula writing, just all kind of jumbled up together. This is where things get interesting, because just based on what we call the compound, you need to decide what the thing is. Is it ionic? Is the thing covalent? If it's ionic, what do we have to do with it? Well, if it's ionic, maybe there's a polyatomic in there. Maybe the thing is multivalent. What do we do with that? If it's covalent, well, the covalent's easy. Covalent means there's no charges that we care about. We need prefixes to tell us what's going on. And believe it or not, for some of you, I didn't realize this until I ran into it in the other class. For some people, the worst thing I could absolutely do to you is give you the common name. What happens if instead of an ionic name or a covalent name, I give you a common name? What if I tell you you're reacting something with bleach, or stomach acid, or battery acid, or what other common names can I give you? Table salt. I guess they're giving you some of these common names, and now you're like, okay, well, what does that even mean? Some of you might have to Google some stuff. I had a student, at least one student, who shall remain nameless in my other class, who couldn't tell me what water was. The question said, this reacts with this plus water is this. You know, well, what's the formula for water? A couple episodes of Magic School Bus, or some of your elementary school career, should have told you that water is H2O, but that might be new to you, and that's fine. But there are common names that you need to become familiar with. So what we're going to do is we're going to take what you're given, and we have to build all the formulas for each individual piece. And then you'll balance. So after you've got all the individual name pieces, you're going to make your skeleton equation, and you're going to balance stuff. Today, I'm going to relax the restriction on balancing. I'm going to give you the questions. All I want you to do is build them. You don't have to do any balancing today. But you will soon. Again, here's a bit of an aside. When we use certain element names, those elements just show up as they are. For example, if I tell you you're reacting something with iron, iron is just, it's a metal. It's an element unto itself. If you have a pile of iron together, each of those individual atoms of iron are just hanging out together. It's just Fe. But there are some that are not content to just hang out on their own. Something like Fe, because Fe on its own will charge positively, sorry, not on its own, because Fe will charge positively, when it's on its own, if it doesn't have anyone to give those extra electrons to, they will just stay. Iron is totally content, all of the metals, any positive ion is totally content to just hang on to whatever it has. So when iron's on its own, it's just Fe. If someone comes along and says, hey, I want those, it'll say, okay, do you want 2 or 3? But on its own, it's not going to force anything away. Something like oxygen, on the other hand, oxygen on its own wants. Oxygen's a taker, oxygen's not a giver. And when you have if you are reacting something with pure oxygen, because every oxygen on its own wants more stuff, I want what you have and you want what I have, they're going to have to do what? What do you think I have to tell my 2 and 4-year-old when they both want the same thing? They have to share. And they do that on their own. If oxygen's hanging out with other oxygens, let's take a look at what they do again. Let's draw a couple Lewis diagrams here just to get a picture of what's happening. On its own, this is what a single oxygen will look like. So if I have a whole bunch of oxygen atoms, what are they going to start to do? Each oxygen wants to gain 2 electrons. This one wants 2 more, this one wants 2 more, and they're coming from other places. So we've seen when we drew the Lewis diagrams, we said they share. So those 2 are going to share, these 2 are going to share, and what they're going to do is produce something that looks like this. That's why we do Lewis diagrams. Each of these shared pairs is represented by one of these lines. And now I've got 2 stable oxygen atoms bound together, or ions rather, bound together. And we call this thing oxygen. That's an atom of oxygen. That's an atom of oxygen. This is also just oxygen. And so it's understood when we use some of these names, there's a group of chemicals together that group together, that when we use their name, we don't mean the individual atom, because these things don't exist on their own as individual atoms like iron would or any of the metals. They exist together, bound, and so you're going to get a formula for this thing that's O2, and we call this thing oxygen. So there's a group of elements that will do this on their own, and you need to know what these elements are. You need to just straight up memorize them. They are called the diatomic elements. Di means 2. It's a prefix we've looked at before. And there's a family of elements that are diatomic. Oxygen is one of them. This guy right here. Here's a picture of the periodic table. I'm going to start coloring some of these things in. Blue might not be a great picture or a great one. Can you see blue if I color it in on the screen? Okay. You go ahead and turn this on. I don't know if that's better or worse. Okay, oxygen is one of them. There are 7 that do this. Oxygen naturally exists only as a diatomic element, is this blank right here. The other diatomic elements are hydrogen, nitrogen, fluorine, chlorine, bromine, and iodine. Those 7, when they're on their own, are so grabby and so possessive, they will bind with other of themselves to stabilize themselves. So you get this group right here. There are 7 of them. They kind of form a 7. They also, someone else told me once, oh, it's like a hockey, it's the hockey stick and puck. Sure, whatever. However you want to choose to remember these things. And if you look at your periodic table, they are also conveniently colored in for other reasons, but they are colored in. Hydrogen is colored in because it's a gas. So is nitrogen, oxygen, fluorine, chlorine. Bromine's a liquid, but it's also part of this 7. And then iodine here, iodine's a solid, but it's the one other one that also forms this pattern. And you just need to know, when I use the name iodine, it's I2. When I use the name chlorine, it's Cl2. Fluorine is F2. There are 2 polyatomic elements. Sulfur and phosphorus exist on their own as polyatomic elements. S8 and P4. They just do. I don't have a good reason for why that is. They just do. So, like I said, these 2 bullet points down here at the bottom are just stuff I've said already. A common way to remember the diatomics is to visualize them on the periodic table forming the number of 7 and hydrogen. Or, like I said before, the hockey stick and puck. So when we're going to go build and balance our equations using just these words, here's the process. I'll do 4 examples for you, and then I will leave you to practice. Here we go. So I have hydrogen plus oxygen reacts to form water. On its own, using that word hydrogen, you guys are to recognize that hydrogen is diatomic. It's one of the 7. So when I'm creating the skeleton equation for hydrogen plus oxygen gives me water, hydrogen isn't going to be H, it's going to be H2. Oxygen isn't going to be O. It's one of the few that you need to remember is O2. And all y'all should know that water is, and most of you said it before, H2O. When you're building the skeleton equation, you need to make sure you leave the spaces. You now have to go put these in. You have to put the spaces in so that you can now go ahead and balance these things. So let's balance. I have hydrogens, I've got oxygens, I've got hydrogens, I've got oxygens. You betcha. You betcha. So how do I balance H2 plus O2 gives me H2O? Someone said put a 2 somewhere. Romina, where was that? You just said it? It was you or Savreet? It was you? So where are we putting a 2, Savreet? In front of the H2O. That's going to give me 4 hydrogens and 2 waters. And now what do we go back and do? You betcha. And we're done. And if you want, anywhere there's a blank, you can toss a 1. Okay, nice and easy. But it's the extra step of saying, okay, well, what is hydrogen when it's on its own? It's H2. What is oxygen when it's on its own? It's O2. When you're ready, flip the page. Okay, so here is a little bit of stuff to get you primed. We just did number 1. Don't worry about number 1. I am going to do 3 more examples for you off this page just to get you kind of in the zone, and then you're going to go. I am not going to make you balance today. I just want you to build. The balancing will come back again in a couple days. We're going to do number 3 as an example, number 5 as an example, number 7 as an example of how you go through the process of building these things. 3, 5, and 7. Here we go. Word equations. I've got sodium. Sodium plus water reacts to form sodium hydroxide and hydrogen. This is a reaction you've seen before, or you should have seen before. If you had me or my student teacher last year, we did this. If you had Mr. Easton, he did this. If you had Mr. O, he did this. Well, he didn't do it. He had someone in the lab do it for him. If you had Miss Gill, she's too scared to do it. She told me that. She didn't do it. You take a chunk of sodium, you toss it into water. What happens? What do you remember from grade 9? It's one of the more dramatic reactions you see in grade 9. Sodium metal, when you toss a chunk in water, goes... Sorry? It does a whole lot more than that. It blows up. It's an explosion. It goes boom. Well, why? Why does sodium metal explode in the presence of water? Well, it reacts very quickly to form sodium hydroxide, produces a lot of heat, and also in the process of doing that, produces a bunch of hydrogen gas. Hydrogen gas, you guys know at this point, is wildly flammable. So the fire that you see, the explosion that you see coming off of this reaction is the burning of that hydrogen. So let's go build this. Sodium on its own is what? It's an element. There's nothing there with it. So what are we going to call sodium? It's just going to be Na. We're going to leave a space out front. Any of the positive ions, so any of the metals, are just going to be what they are. Sodium is Na, you just leave it as Na. No charge. On its own, it's just an atom. Plus water. Y'all should know at this point that water is H2O. The arrow is there. Now sodium hydroxide. We actually have to go now and build this thing. Sodium hydroxide, it's a compound. Is it ionic or is it covalent? It's ionic because sodium has a charge of +1 when it forms a compound, and hydroxide is a polyatomic ion. Hydroxide is OH, has a charge of -1. So when I'm building the formula for sodium hydroxide, what's the formula going to be? It's just going to be NaOH. Because if we take a look here, if the charge, if this is +1, this is -1, I only need one of each to balance those charges. Cool, we've done that piece. And now we've got hydrogen. Hydrogen on its own is, it's not H. It's diatomic. It's H2. And so then if I asked you to at this step, you'd go ahead and balance. Yes, Brooklyn? You have to, yes. Any of the diatomics, when they're on their own, always have to have the 2. Phosphorus on its own will have the 4. Sulfur, if it's on its own, is going to have an 8. P4 and S8. When they're on their own, because of how they form ions. So like oxygen has space, oxygen has space to share 2 electrons. So it's going to find another oxygen, it's going to buddy up. The sulfurs get more complicated because the sulfurs are further down. For reasons that you might look at in Chem 11, sulfur goes S8, phosphorus goes P4. For reasons that I can't tell you yet. I mean, I can, but it would just make things more confusing. I'm just not going to. Take my word for it at this stage. Which I know is really irritating for some students. I just want to know. Yeah, but it's gross. I'll tell you later. Okay, next one, number 5. I've got potassium iodide plus chlorine produces potassium chloride and iodine. The act of going through this stuff isn't actually that hard. It's just, from what in my experience, it overwhelms a lot of students. They see there's just so much they see to do, and they struggle to break it up piece by piece. If you treated each one of these compounds on its own, like we did before, I just said, okay, what's the chemical formula for potassium iodide? And lots of you were able to do this no problem. Chemical formula, okay, well, potassium. We take a look at the periodic table. Potassium's right there, it's letter K. And because it's with iodide, this is a compound, we're going to have to balance those charges. Potassium is +1. Because iodide ends in IDE, it's just the ion of the element on the table. So iodine is I. What's the charge on iodine? So when I make potassium iodide, the formula is going to be just Ki. I just need one of each. And I'm going to leave my space out front because we're going to come back and balance that thing. Chlorine, on its own, is part of the group of 7. So chlorine on its own is going to have what formula? It's going to be Cl2. It's going to produce potassium chloride. Well, we've already seen these ions already. So potassium is K, charge +1, chlorine is Cl, charge -1. So what's the formula then going to be for potassium chloride? Charges are the same, I just need one of each. It's just going to be KCl. Leave the space out front, so when I get you to go back and balance them, you can. And iodine is going to be I2. Cool. Last one, number 7. Stop me at any point if you have comments, questions, or concerns. Okay, here we go. Magnesium plus copper 2 sulfate produces magnesium sulfate and copper. So let's go ahead and build these things. Magnesium on its own is what? I'm so glad you said that. It's not. But I'm very happy you said that, because there was a whole conversation we had in the last block that if you hadn't said what you just said, I wouldn't be able to have again with you guys. But you just opened the door into a fantastic conversation I can have with you. It's not Mg plus 2. It's just Mg. No, it's not because of the Roman numeral. Okay. I will. Oh, I am so... Brooklyn, thank you so much. I was wondering how I was going to work that in. I needed someone to make that mistake, and you did me a huge favor by doing that for all of us. Okay, before I go back and address why what Brooklyn said was not what happens, we're going to finish this off. So, magnesium is just Mg. Copper 2 sulfate. The Roman numeral tells you what the charge is. So this is going to be copper. Copper is Cu. And the Roman numerals, the formula writing is nice, because the formula writing, if they give you the Roman numeral in the name, you don't even need to go look up the charge. That Roman numeral is the charge on the copper. So I've got plus 2 here, because it's Roman numeral 2. And sulfate, this ends in ATE. So you're going to go take a look at the polyatomic ion chart. It's ATE, not ITE. So sulfate is what? It's SO4 with a charge of minus 2. Yes. So then what is the chemical formula for copper 2 sulfate? It is, in fact, going to be CuSO4, because if you swap drop the 2 and 2, the last step in swapping and dropping is swap, drop, and? Swap, drop, and? Reduce. Swap, drop, reduce. So if I swap these two 2's, I get Cu2SO4 2, but because both of those are divisible by 2, you have to simplify it. You have to reduce them. So you just need one of each, copper and sulfate, to create a happily balanced ionic compound. Yes, Brooklyn? What plus sign? No. And I'll explain. Oh, yes. The plus sign here, yes. Yes, you do. That needs a gap, that needs a gap. Yes, you do. That plus sign goes there, not that. Yeah, yes. And then, what happens? Well, somehow these guys produce magnesium sulfate. Now, we care about the charge on the magnesium. Why do we care about the charge on the magnesium now and not before? Yeah, Brooklyn. You only need brackets around the SO4 part if you need more than one SO4. Polyatomic ions get brackets when you need multiples of the entire polyatomic ion. Regina, I'm almost done. If you could give me like 2 more minutes, and then you can use the washroom. Yes. Here we are giving the Mg its charge back because it's like what I said about the iron before, right? Right at the beginning when I was introducing this concept. Yeah, magnesium on its own is happy to give, but if there's no one there to take, it will hold on to what it has totally contentedly. And magnesium will just hang out with the other magnesiums and be like, yeah, okay, cool. And here in this compound, copper was happy to give up 2 to the sulfate, and the sulfate's like, yeah, I want those 2. Copper's like, sweet, you can have them, you just have to hang out with me. Sulfate says, fine, I will hang out with you. Then for reasons, in the presence of magnesium, you bring in the magnesium, and for some reason, the sulfate says, you know what, copper? I'm good. You can have your 2 electrons back. Magnesium, come on over. You've got 2 that I will happily take from you. This is the example I gave to my last block class that I was just so hoping I could work into here. Perhaps you've seen this meme before. If my phone loads. Oh, there we go. It's this meme right here. Come on, you. Just wait. No, I'm going to put it on the screen. Hands up if you've seen this meme. This is the distracted boyfriend meme. This is the ultimate insult, right? Like and so here's your question is why? Why does sulfate look at magnesium and be like, I'm done with you, copper. Come on over here, magnesium. This is the exact same scenario. You have a brunette. You have a brunette. Well, but these people are attractive individuals, and for some reason, Buddy walking by in the middle goes, hello. For some reason, copper and sulfate totally happy. Then magnesium shows up, and sulfur becomes a bit of a dirtbag. Or sulfate turns into a bit of a dirt. Why? There are deep chemical reasons for why that, in both cases, there are deep chemical reasons for why this happens. Hormones in the picture. A concept called electronegativity in our case. But the idea is the same. For some reason, in the presence of another option, sulfate ditches the copper it was with and bonds with the magnesium, and now you've got copper all on its own. So this is why, Brooklyn, when magnesium's on its own, it's happy to just be. She was totally happy to just be. And in the presence of magnesium, magnesium will then give up to join. It doesn't get a charge until it gives up. And now copper has been given back the sweatshirt and been broken up with. That's always what happens, right? She gives back the sweatshirt. And now copper's on its own. No charge now, because copper has what it came with. It's got its electrons back. And now magnesium sulfate, MgSO4, is what is created. And that's a really common thing that I see students do. I see students writing the charges on the individual metals all the time. Don't. They don't get those charges until they bond. And even then, you don't write them, you just use them to create the new compound. Mg is going to give to the SO4, but when they come together, you get MgSO4 plus Cu. The distracted boyfriend meme is it's a good example, but the metaphor does fall short. Because in this case, the copper is actually happy to get away. The copper would rather get away. So in that case, it breaks down. As soon as you learn a little bit more chemistry, you'll be like, that meme didn't quite work. But in the interim, it works just great. The chemistry wasn't there. It's true. Okay, so that is all of the examples I'm going to do. Any comments, questions, concerns about what I've just done? Okay, so then I want you guys to practice a bunch of these things. Do not balance. No balancing yet. I just want you to build. Here are the questions I want you to do. I want you to do 2, all the ones I didn't do. 2, 4, 6, and then 8 through 12. So there's 8 questions there. And in addition, I would like you to mosey your way over to the desk in front of Matthew and grab that piece of paper. I forgot to include it in your booklet. There's 8 more questions like this for you to build. That is the rest of the class and your homework for the weekend. I'll take them up on Monday. Grab one of those. I'm here to help. On your markets, a go.